We're going to continue drawing Lewis structures. Now we're going to look at molecules that end up with multiple bonds between atoms in the final Lewis structure. So let's look at the molecule C2H4, which is called ethene, or its common name is ethylene, right? And if we're drawing our Lewis structures, then we draw our connected structure. And in this one, the carbons are connected together. And I will tell you up front that the hydrogens are spread between the two carbons, right? We could have gone trial and error, right, to get there, but I'll go ahead and start with that, okay? So now we look at our valence electrons, right? Our valence electrons, 2 carbons, that would be 2 times 4, and our 4 hydrogens would be 4 times 1, right? So that's going to be 8. That's going to be 4. So we have 12 valence electrons to distribute. In our bonding, right, we've got 1, 2, 3, 4, 5 bonds shown. So that accounts for 10 of those valence electrons, leaving only 2. We can't put those around hydrogen, right, because hydrogen only has space for 2 electrons around it. And so we have to put those 2, since we distribute them in pairs, on one or another of the carbons. And so I picked the left one, right? So at this point, we're out of electrons, but here we have an atom without an octet, okay? And if we go through and look at the formal charge, right? So the formal charge on the carbon with the unshared pair, right, is going to be 4 minus 2 plus half of 6, right, which is -1. And the formal charge on the carbon without the unshared pair is 4 minus 0 plus half of 6 equals +1. So not only do we have an atom without an octet, we have 2 atoms with formal charges. The left atom has a formal charge of -1. The right atom has a formal charge of +1. And even though that adds up to 0, right, we would prefer it if we could come up with structures which have the least number of formal charges possible. And so one thing we can do then is we can let these 2 electrons be shared between the 2 atoms, right? So we can redraw our Lewis structure. Putting a second bond between the 2 carbons, right? Now if we go through and do our formal charge calculation, right, for each of those carbons, right, the formal charge, since they both look the same, would be the 4 that they brought minus 0 unshared electrons plus half of the 8 electrons in bonds attached to those. That equals 0, right? So now all the atoms in our structure have 0 formal charge. All the atoms have an octet. And so this is the preferred Lewis structure, right? So we can share extra electrons when it both gives other electrons an octet, and when it reduces the formal charge in atoms that we see initially. Now let's consider HCN, or hydrogen cyanide, a very poisonous gas, right? Now, I will tell you that in this case, the formula is telling us something about the relationship. And so there is the connected structure. If we count up our valence electrons, right? Hydrogen has 1, carbon has 4, nitrogen has 5. That adds up to 10. Right? We've got 2 bonds there. That accounts for 4 of those, leaving us with 6. We start around the outside. We can't put any on hydrogen, and so we can put all 6 around nitrogen. We're out, but that leaves carbon with only 4 electrons around it without an octet. And so nitrogen can share 2 of those. And so we can draw another structure, right? We have to redraw this, where there is a triple bond between the carbon and the nitrogen, leaving 1 unshared pair on the nitrogen. And that is an acceptable Lewis structure for the hydrogen cyanide molecule. Our next molecule is CO2, the carbon dioxide molecule, right? So again, oxygen is more electronegative than carbon. That's going to put the carbon in the center, the oxygens off to the side. If we deal with our valence electrons, we count up our valence electrons, right? Carbon will give us 4. Our 2 oxygens will give us 2 times 6. That's 4. That's 12. Leaves us with 16 total valence electrons to account for, right? We have 2 bonds there. So we already know where 4 of those are. Leaves us with 12. And so if we start distributing those, starting on the outside atoms and working in, we get something like this, right? But again, we have this situation where the central carbon only has 4 electrons around it. It would like to have 8. But really we have, right, 2 choices, right? The last time we ran into this situation, we took both pairs of we took 2 pairs of electrons from one atom and made a triple bond. But we also have the choice here, because there's unshared pairs on each side, of taking 1 pair of electrons from each of the oxygens and sharing. And so how do we tell which is the better choice? Because each choice would give the central carbon an octet. And again, it's going to come down to formal charge. So let's draw each of these, right? So if we chose, if we go with the choice from the green arrow, we're going to get something like this, right? This oxygen we didn't disturb. The central carbon now would have a triple bond to this oxygen, and that oxygen would have an unshared pair. If we choose the blue arrows, this oxygen would have a double bond to the carbon, but still have two unshared pairs. This oxygen would have a double bond to the carbon, but still have two unshared pairs. Now, which of those is better? It comes down to formal charges on the oxygen, right? So if we look, I'll have to be small here. So our formal charge on the oxygen on the left is going to be 6 minus 6 plus half of 2, which is -1 for the left oxygen. The formal charge for the oxygen on the right is going to be 6 minus 2 plus half of 6 equals 6 minus 5 equals +1. So in this structure, the oxygen on the left has a negative formal charge. The oxygen on the right has a positive formal charge, right? So now if we look at the bottom structure, both of the oxygens have the same structure. So if we look at the formal charge on either oxygen, it's going to be the 6 electrons, valence electrons oxygen brought to the party, minus the 4 that they have without sharing, plus half of the 4 that they are sharing with other atoms, right? So in the bottom structure, each oxygen has a 0 formal charge, making this bottom structure preferred over this middle structure. And so this is our preferred stable Lewis structure. Let's look at another example, right? Let's look at SO2, or sulfur dioxide. Again, oxygen is the more electronegative atom here, so sulfur has to be in the center. Right. If we look at our valence electrons, right, sulfur contributes 6. 2 oxygens contribute 2 times 6. So that's 6. That's 12. Leaves us with 18. Right? Because of bonds, you have already accounted for 4 of those, leaving 14. We start around the outside, distributing in pairs. And we don't run out until we have 1 unshared pair on our sulfur. We've accounted for all 14, leaving us with no valence electrons to distribute. Right? Now, one problem we can see immediately is that sulfur in the center, 2, 4, 6. Sulfur doesn't have an octet, but atoms around it have unshared pairs. Right? The other problem we can see with our structure, right? If we look at our formal charges, and we've done this enough, I'm not going to go through the math, right? The formal charge on each oxygen here is -1. And the formal charge on sulfur is +2, right? And so we've got two issues. We've got an atom without an octet, and every atom in our structure has a formal charge. Well, one way of reducing a formal charge is to share electrons. So if this oxygen shares a pair, and this oxygen shares a pair, that will reduce the formal charge of both oxygens and also neutralize the positive formal charge of the central sulfur. And so we would end up then with a structure like this. Where each oxygen retains two unshared pairs, but has a double bond to the sulfur. And again, remember, we can do this even though sulfur has 2, 4, 6, 8, 10 electrons around it. Sulfur, being in period 3, has the space for extra electrons. So in this case, sulfur takes the extra electrons to reduce its formal charge, and it can do that because it's in period 3. An interesting case is BF3, boron trifluoride. Okay? And so, again, fluorine is our most electronegative element, so it can't be in the center. So the boron has to be. So we put our fluorines around it. Right? If we do our valence electrons, right? Boron gives us 3. 3 fluorines gives us 3 times 7. So that's 3 plus 21 is 24. We've already accounted for 6 of them because of the bonds, leaving us 18. And so we distribute those 18 around the fluorines, and we run out of electrons right there. Okay, now the question then becomes, right, we've got this boron in the center, but it doesn't have an octet. And so when we've run into this situation in the past, we've dropped a pair of electrons from an adjacent atom with an unshared pair to give that an octet. And so we have to also consider this kind of possible structure. Right? Versus our original structure that was like this. Okay, so we've done this enough times. We shouldn't have to go through it, but if, you should test me, right? In the left structure, in the red structure, this boron would have a negative formal charge, and fluorine would have a positive formal charge. In the right structure, everything is 0. Right? So here's our question. Do we go formal charges so that the central atom gets an octet, or do we leave the central atom without an octet so that none of the other atoms have formal charges? Well, here's the issue, right? Fluorine is a very electronegative atom. Electronegative atoms, if they have to have formal charges, would prefer those formal charges be negative. So to get an octet, we have to give this electronegative atom a positive formal charge. And oh, by the way, boron is a relatively electropositive nonmetal atom. So we've got this electropositive boron with a negative charge. In this case, right, that creating those formal charges counter to the nature of those atoms makes that less stable. And so we consider this the preferred Lewis structure, even though that central atom doesn't have an octet, right? So especially if we have small atoms or electropositive atoms in the center, right? If giving something an octet gives electronegative atoms a positive charge and or electropositive atoms a negative charge, that then is not preferred, and we live with the lack of an octet, right? So those are some situations in terms of creating multiple bonds and situations where we don't want to create multiple bonds between atoms.